Well, we haven't really done anything challenging yet with our kinematic equations, not particularly challenging. So let's take a look at this fun little free simulation offered by the PhET website, that's Physics Education Technology. I just typed in PhET Projectile Motion in order to find the simulation. Looks like we've got a cannon on a raised platform. There's a launch button here. Let's check out what that does. That's fun. So this is a lot like that artillery game. I can erase the trajectory and start over. Can we adjust the launch angle here? Aha! Now, unfortunately, if you look, we can only adjust the angle in increments of 5 degrees. I tried typing a number in there. That didn't seem to work. And that's going to be a bit of a problem later on. We can also adjust the height of the platform and the launch speed. So there's a whole bunch of variables under our control. In fact, there's one more here, the location of the target. So there's a bunch of different ways that we could turn this into a good two-dimensional constant acceleration kinematic problem, and that's what we'll do. I think I'll pick two examples here. And the first example, if you were to sit down and turn this into a problem, I'm sure you would realize before long that there are a variety of ways you could go about it. If you let's say you've only got one equation to work with, that's your only problem-solving tool. If you've only got one equation, then you can only have one unknown. So you'd have to write a problem where only one of these various quantities was unknown. Now, we've got our constant acceleration kinematic equations. That's a set of equations. So since we have multiple equations, it's possible that we could have multiple unknowns, and the problem would still be solvable. But remember, one of those equations, the v-squared equation, in fact, let me go back to that set of equations here. Here are the constant acceleration kinematic equations. Remember that this one came from combining this one and this one. Maybe you recall I solved this one for the time interval, I plugged it into here, and I skipped the algebra, but if you simplify, you wind up with this equation from which the time has been eliminated. So we definitely have two independent equations that we can use, and this is not really a separate equation. Both of these equations give the displacement. We also developed this equation by using the definition of average velocity. Right? Displacement is always average velocity times time interval. And for the special case of constant acceleration, this is how you can calculate the average velocity. So I'm going to go out on a limb here. I'm like 99% sure that this set of equations is really only two independent equations. And so I would expect any two-dimensional projectile motion problem to only be solvable if there are at most two unknowns. One of the nice features about this simulation is that you can change what you're launching. Right now it looks like we're launching, what is that, a pumpkin? Not a very big pumpkin. What else do we have here? Cannonball. That's traditional choice. Ooh, a piano, I like that. I'm not in favor of smashing pianos, but that's dramatic. Ooh. And conspicuously missing from this list is a kitty cat. I don't know what they were thinking, but we can launch a person. Whoops. Human. Head first. Okay, no helmet. Oh, he does have a helmet. All right, let's turn this into a problem here. I have chosen to elevate the platform to 11 meters, and I will put the target 15 meters from the base of the platform. There we go. I'll go with a launch angle of 65, kind of steep there. All right. And to start, I'll just pick some arbitrary speed, launch speed. Let's fire the cannon and see what happens. I'll go with the human. I'm feeling a little sadistic here. Whoa. We can zoom out. Way off, totally missed. Should I increase the speed or is that going to make it worse? Obviously that'll make it worse. Let's go with the lower speed, much lower. Barely plopped out there. One more time. Not much closer. So we could keep fiddling with this until we find the appropriate launch speed that will get us to the target. Now, something you should be thinking about as you watch this here is there a single value of the speed that will work? Or are there perhaps multiple speeds? You know, it's kind of clear that there's a range of speeds. If you could find the one speed that got you directly at the target, assuming there is one speed, then any speed close to that speed should get you within the outer edge of the target. But is there a single value of V naught that will land you in the bullseye? My intuition as I watch this tells me yes, because as I go on the low side and the high side, I'm missing to the right and I'm missing to the left. So that leads me to believe that there's a single speed. And the math that we have to deal with will tell us whether that's the case. Okay, so if all of those variables are fixed, the height, the initial height, the launch angle, the distance to the target, and of course we know the acceleration because we have not included any air drag here, then can we solve for the required speed to hit that bullseye? And I'm going to do this on paper. We'll draw a crude diagram, we'll choose our coordinate system, and we will apply our kinematic equations. All right, so let me start by drawing the coordinate system. That's probably the first thing you should do. Just make a really rough sketch. So here's the platform, here's the ground, and I'm just going to indicate, I'm not going to worry about the fact that the cannon has spatial extent. Let's just pretend the cannon launches from right here. So this point is where the cannonball or the human leaves the cannon and they are now in free fall. As long as they're within the barrel of the cannon, they're still being pushed by something other than gravity. So this is the point where free fall begins, and we would like to hit the target right here. Remember, we've got an initial velocity vector, which is tangent to the trajectory at the point of launch. So I will label the length of that velocity vector V naught. That's really your initial speed. And then we've got this launch angle theta, which is given. I can label the height here h. And notice this does not constitute choosing a coordinate system. I'm just indicating that this length here is h. I haven't talked about whether it's a displacement up or down. Now, I see two good choices for your coordinate system. You could put the origin at the point of launch. You could put the origin at the base of the pedestal there. You could even put the origin at the target. I think that's a less convenient choice. Any other arbitrary place, like why would you put the origin here? That makes no sense. So I'm going to put the origin actually at the base of the pedestal. You do not have to do that. Remember, the physical results that you get do not depend on your choice of coordinate system. The number that you get at the end may depend on the coordinate system, but the physical interpretation does not. I'll go with up as positive. Again, you don't have to do that. You could have put the origin here and said that down was positive y, and the advantage to that is that your acceleration in the y direction is then plus g, but either way it works. So y-axis, x-axis. And over here I'll say given, well, we know the height h, we know the angle theta, and I forgot to label, let's go with d for the distance from the base of the pedestal to the target, and that has already been fixed. The way I've written the problem right now, it's already been fixed. And we'd like to find the required speed V naught. Okay, and there's really one other known quantity that I did not include here. It's kind of implicit. We also know the y acceleration, because if we're pretending that there's no air drag, then the vertical acceleration is the gravitational acceleration. Okay, so I recommend having a sheet like this, unless you're really a pro and you've got all those equations right in the front of your mind, you can see them. Have a set of equations ready so that you can gaze at it and decide which of these equations, maybe it's one or maybe it's two, that will get you to the answer you want as quickly as possible. And I'll warn you, for this problem, it's not as obvious. We're jumping right into a couple more difficult problems here. for projectile motion? Well, we're interested in the initial speed, which is the length of this initial velocity vector. And don't forget that that velocity vector has components. And I can label those components v naught sub y and v naught sub x. And I'll remind you, I guess I better get a fresh fresh, I got pizza on the brain. Fresh piece of paper here. Is paper fresh? Okay, initial velocity vector, here's the components. That's pretty sloppy. We've got an angle that we call theta, and notice that angle has been measured clockwise from the positive x-axis. And that means we can use these formulas. V naught y, the y component would be the hypotenuse times the sine of theta, and the adjacent side, the x component of the velocity, would be the hypotenuse times the cosine of theta. So we do know the angle theta in this problem, but we don't know the hypotenuse of the triangle, which means we really do not know either of the velocity components initially. Those are both unknown quantities. But, yeah, it's kind of, think about it. Yes, it's two unknown quantities, but they both have a known quantity in them. So really, between these two unknown quantities, there's only one unknown. That would be the speed. So I would say, yes, there are two unknowns. Not in this triangle, not in the velocity triangle. When it comes to the initial velocity vector, there's only one unknown number, and that would be the magnitude of the vector. We do know the angle it makes. But there is a second unknown in this problem, because you notice nothing has been told to us about how long it takes the cannon to strike the ground. So when we go back to these equations, I can identify two unknowns in here. We don't know the time interval, and we don't know the initial launch speed. Now that doesn't necessarily mean that we need two equations. Two unknowns does not necessarily mean you have to use two equations, because what if the problem is only asking for one of those unknowns? Notice we're not being asked to find the time, we're only being asked to find the initial speed. So if we had a single equation that could get us to the speed directly, then we could just use that one equation. But I'm already recognizing as I look at these equations, none of these equations show us v naught without the use of delta t. Notice how this equation has velocity and time in it. Let me skip this one for a second. This one has velocity, initial, and time, so we would have to know the time if we want to solve for velocity. This one, velocity, well, yeah, because it's got initial velocity inside the v-bar and the time interval. So maybe you're thinking, why can't we just use this one, right? Well, let's think about that. I've written this in the x direction, but remember, this equation is applicable along any axis. So let's apply it along the vertical axis. We do know the y acceleration, that's going to be negative g. Do we know the y displacement? As a matter of fact, we do. Between launch and striking the target, we do know this vertical displacement, so we could plug that number in right here. And what about on the left side? How many unknowns are on this left side? Well, when you apply this along the y-axis, this would really be the final y component of the velocity. So when the cannon strikes the ground, it's got a velocity tangent to the trajectory. We do not know the vertical component of that final velocity, and we don't know the initial component either, because we don't yet know the launch speed. Yes, we know the angle, but we don't know the magnitude. So this equation, as a matter of fact, does have two unknowns in it. We can't solve it for the initial y component of velocity because we don't know the final y component of velocity when it strikes the ground. So no single equation here will get us to the result we want. Darn it. That means we're going to have to use two equations. Now remember that remark I made about how you can often go to one axis or the other to figure out how long your projectile is in the air, and then take that expression for the time and plug it into the other axis. That's just a general tip that seems to be effective in many of these two-dimensional problems. So it's not always necessary to see the way forward. You know, very often you're not going to look at a problem and be able to recognize immediately how to proceed. So my advice is just start writing a couple of your equations, plugging in what you know, and then after that, often the way forward will become a little clearer. So I'm going to first look at the x-axis. And I will apply this kinematic equation between two times. So let me label the times here. Let's go with t0. That's the launch time. And because I've already worked this problem, eventually I'm going to go back and figure out something about the apex here. So t1 will be when the projectile reaches the apex, that's the highest point, and t2 will be when we strike the ground, or the target. Remember, we're trying to figure out how fast we have to launch at a particular angle to get to the target. Okay, so by labeling these times, it just makes it easier to set up the rest of my problem. I really advise that technique, especially when it comes to showing your work so that I can give partial credit. Okay, let me apply the equation for displacement along the x-axis between the initial and final time. So right now I'm looking at the motion from beginning to end. I don't care about that middle time right now. So I will say the x-coordinate at time 2 minus the x-coordinate at time 0 equals, that's what this displacement is, final minus initial, equals the initial coordinate. Now, we always have to insert additional subscripts to specify which axis we're talking about. So I want the initial velocity along the x direction, which would be the velocity at time 0 along the x direction. It's the x component of velocity at time 0. Okay, and then times t2 minus t0, it's time interval. And I might as well, I should have said this, let's just set that equal to 0 seconds. That's almost always the best choice, just to simplify your algebra. And then, what's the x acceleration? I talked at length in a previous video about the advantage of choosing a coordinate system where your y-axis is vertical and your x-axis is horizontal, because what is the component of gravitational acceleration along the x-axis? For that choice, the component along the x-axis is 0. So we don't even have to mess with 1/2 at squared. So I can just say plus 0. All right? And now let's plug in what we know. I can cross out t0 because we just decided to call that 0 seconds. Well, x2 minus x0, that's the final x-coordinate minus the initial x-coordinate. That's really the displacement in this direction. That's a positive displacement with the magnitude of d. So I can really just say plus d. Now, if you don't like doing it that way, you could say, since this is the origin, the coordinate of this point is d, and the coordinate of this point is 0. D minus 0 is d. You can think about it either way. Now remember our velocity triangle? The initial x component here. Oops, this is supposed to say x. I'm sure you caught that. V naught x is hypotenuse cos theta. So I could plug this in now, but it turns out that makes the algebra just a little more cumbersome. So for now, I'll just leave it as V naught x times t2. Okay. Now remember, by assumption, we're given the distance to the target. So we know this number, we don't know this number, we don't know this number. So I can't actually solve this equation for one of the components of the initial velocity vector, but I can solve it for t2. And t2 is what you might call the time of flight. It's the time interval from launch to striking the target. So t2 really is the time of flight. And I may not know what that number is, but I know how it depends on how far away the target is and the x component of the velocity. And I'd like to interject here. Many of your homework problems are definitely easier than this particular problem. But if you can do this problem, you're pretty well prepared for a two-dimensional kinematics. You just want to get as much practice as you can here. Let's take that now and perhaps plug it into an equation along the y-axis. So which of these equations should I evaluate along the y-axis? Remember, I do know the overall vertical displacement for the y-axis. I know the y-acceleration, but I have two unknown quantities. So I just have a suspicion that this is not going to make my life easier. If I, also note there's no t in here. So the expression that I just found for t, I can't substitute that in here. So how's about I substitute it in here? Let me evaluate this equation along the y-axis. So for the y-axis, I'd say delta y, final minus initial. Again, let's go with times 2 and 0. So y at time 2 minus y at time 0 equals v naught t. Well, now it's the initial component of velocity along the y-axis, which is v naught y times delta t. And just like before, my delta t is really t2 minus t0, but t0 equals 0 seconds, so that's just t2. And now let's be careful here. 1/2 at squared, that's plus 1/2 times, because I went with the choice of up as the positive y-axis, my y-acceleration is negative g. Don't forget that negative sign. And delta t squared, that's just t2 squared now. Okay, are we making progress here? Is this getting us closer to where we want to go? What quantities do we actually know here? Of course, we know g. We don't know the initial component of the velocity because we don't know the initial launch speed. That's what we're looking for. We also don't know the time, but check it out. We at least have an expression for the time. Now the displacement in the y direction, that's actually going to be negative h. We end here. We started here. That's a vertical displacement of h in the downward direction. You can also see it by saying y final is 0, right? Because it's at the origin, or it's on the x-axis, and y initial is plus h. So 0 minus h is negative h. I'm just going to say, hey, the displacement's in the negative direction by h units in distance, so it's negative h. And then initial y velocity. I think I'm going to switch over to some bolder pens, by the way, to make it easier to read here. The time is d over v naught x minus 1/2 g, and then I've got t squared. So that's d squared over v naught x squared. And this is starting to look kind of messy. And I'm perfectly willing to admit, the only reason I kind of know where this is headed is because I've done a lot of these problems. I've seen this problem before, or a very similar problem. Remember what we're looking for. We want the length of the initial velocity vector. That's the launch speed, how fast we have to launch it to get it at that target. Because if we launch it too fast, it'll go over here. Too slow, it plops down over here. Now, if we could find both of these components, the initial velocity vector components, we could use Pythagorean theorem to find the initial speed. I see both of those components in this equation. So maybe you're thinking, well, you can't solve one equation for two unknowns, and that's true. I would need a second equation. But check it out. We can express each of these components in terms of the desired hypotenuse and the angle, and we know the angle. So if we use these trig expressions here to rewrite all of the velocity components initially in terms of speed and angle, we will actually have a single equation in one unknown. That's what we want, because we know theta. It's not really clear how that's going to look algebraically, but let us proceed here. Okay, so I think I'll do this now. Watch this. The tangent of theta from this triangle, the initial velocity vector triangle, would be the opposite component, that's v naught sine theta, over the adjacent component. Notice that the magnitude cancels and we just get sine over cosine. What am I doing here? I'm going around in circles. Boy. Okay, this is what I meant to do. V naught, yeah, I'm definitely going around in circles. Tangent of theta is v naught y over v naught x. Right? This is v naught y, which is the opposite side. This is v naught x, which is the adjacent side. Take the ratio of those two sides. By definition, that's the tangent of the angle. What I was about to do is recognize sine over cosine is tangent. rewrite it as tangent, and I get the equation tangent equals tangent. We already know that. Okay, so anytime you see this ratio, initial y velocity component over initial x component, that is the tangent of the launch angle. And I do see that here. So I'm going to rewrite that as the tangent of theta because we know theta. Remember, it was given as 65 degrees. Okay. And let's see here. Negative h equals, this is really d times tangent theta. So I'll write it as d tan theta minus 1/2 g d squared over, now in the denominator, we have v naught x squared. V naught x is the initial speed times the cosine of theta. So I really have to write v naught squared cosine squared theta. What am I solving for here? Initial speed. So we're practically done. The algebra is not as clean as some of the simpler problems we've looked at so far. We haven't looked at too many problems, but at least you can see this is totally doable because if we return to our list of known quantities, I specified the height in the simulation, I specified the angle, I specified the distance from the base of the pedestal to the target, and we know that g is 9.8. So the only unknown in this equation is v naught, and now it's just what I like to call an algebra problem. Have you ever wondered where that awkward word algebra comes from? That word doesn't look a lot like other words in English. Well, I read about it, and I guess it was it an Arabic scholar? This is like 1,000 years ago. Somebody wrote a paper in that part of the world that was pretty foundational in the history of math and, well, the history of algebra specifically, and this phrase is in the title. So I guess our anglicized pronunciation is algebra. I call it algebra. So let's do some algebra here. I would like to put this term on the other side, and I'll move the h over. So I get 1/2 g d squared over v naught squared cosine squared theta equals h plus d tan theta. I'm just moving stuff around. And my goal, of course, is to isolate v naught. So I'm going to get rid of all this garbage simultaneously. I will multiply by 2. I will divide by g. I will multiply by cosine squared theta, and I will divide by d squared. And that will leave me with the reciprocal of v naught squared. So out front here, what do I have? 2 cosine squared theta over g d squared. I believe I did that right. And don't forget I still have this quantity. Ugh. And maybe you're thinking, why don't we just plug in numbers here? I don't want to do all this algebra. Just evaluate these in your calculator and then solve for v naught. Well, you could do that, especially on your TI, but I don't recommend it. One reason for doing it this way, if you can, is the more steps you show, the more partial credit you can get if it was an exam problem. Or if you're doing homework, the better able you are to review your work and figure out where you messed up. If you stopped here, or even at the previous step, plugged in numbers, and got the wrong value out of your calculator, I'm not going to know that, and so I just won't be able to award credit for that. Okay, now let's take the reciprocal, and I'll do the square root all at the same time. Okay, so when I take the reciprocal and the square root, this junk turns into 1 over the square root of h plus d tan theta. And what do we have here? After I flip it, well, when I take the square root, the cosine squared over d squared just turns into cosine over d. So I think I'll put that out front. So I've got a d over cosine. Remember, I'd have to reciprocate and take the square root. And then I'd be left with root g over 2. I admittedly, like I said, this problem's a little challenging with the just the algebra is one of the things that makes this problem challenging. And then if you've got plenty of opportunity left to screw up because you have to know how to do order of operations correctly. This isn't a math class, but that final step is worth some points. But if you got this far and then failed to plug in numbers correctly, you would at least get most of the credit. Okay, I'm going to attempt to do this all at once here. Remember, the height I chose was, I went with, I think it was 11 meters. The distance to the target was 15. I chose a launch angle of 65 degrees. And I'd like to know what the required speed is to get it to the target. And I'm looking at this here and recognizing that technically, when you solve this equation, there are two solutions, are there not? Like, how many, let's see here, just a very brief math review here. How many solutions are there to this equation? One. The usual convention is when you write a square root sign and then 9, you're referring to the principal or positive root. So this is like saying x equals 3. Now this equation, x squared equals 9, has two solutions. X would be plus or minus rad 9, which is plus or minus 3. Right? Negative 3 squared is also 9. So when we look at this equation, the same thing would apply. Mathematically speaking, you can find two values of v naught that would satisfy this equation. But what does it mean to have negative speed? That's not physically meaningful. In this, the theory that I don't think you could even call it theory, but the kinematics that we're discussing here, it's assumed that speed v naught is a positive number. So we've now answered the question that I posed earlier in this video, which is, are there multiple speeds that will get you to the bullseye? And the math is telling us, no, there's just one. Only one number will come out of the calculator here. All right. Let's see if I can get my order of operations correct. Here's what I'll do. I'm going to evaluate the denominator, and then I have this 1 over x button that I'll use. So I'm going to make sure first that I'm in degree mode. You can't read that, but yes, I'm in degrees. So 65, I hit the tangent button. Your calculator may be different. I multiply by the distance of 15, and I add the 11 meters. I hit equals. Then I take the square root, and now I need to flip that. So I do the reciprocal. All right. And this is a little awkward. I'll multiply by 9.8 square rooted divided by 2 square rooted. Then I have to multiply by the distance, again, of 15. And then I have to divide by the cosine of 65. So you notice on my calculator, I punch in the angle, then I hit cosine. It may be different on your calculator. You may have to use parentheses. So you want to get some practice. 11.958. I'm just going to round that to 11.96 since I don't think I can adjust the speed out to the thousandth of a meter per second anyway in this simulation. All right, moment of truth. Let's see if these kinematics work. Or at least let's see if whoever programmed the simulation used the same kinematic equations, right? We're not actually doing this in nature. We're not going to go outside and launch a person out of a cannon. We're going to see if the person who programmed this simulation used the same physics. I'm reluctant to even call it physics because we haven't even talked about force yet. We're really just doing math here as preparation. So back to the simulation. Here we are. Okay, 15 meters for the target, 65-degree launch angle, 11 meters above the ground, and now let's adjust the speed. 11.96 is the value we found. Well, I can't be doing any tenths of a meter per second. I'm restricted, to integer values. 11.96 is very close to 12. I expect this to work. And let me zoom in here. Erase. Can I do a drum roll simultaneously? Let me see if I can do that. All right. Yeah! Okay, I never hit a home run in a Little League, but at least I can do that. That's sort of satisfying. I don't think I'm going to get a trophy for that, though. Okay. Can we do anything else with this problem? Remember, I didn't, the way I posed the problem, we were not being asked for a time interval. But let's just Since we've got a couple unknown quantities here, let's tack onto this problem just a little bit and ask ourselves, what's the highest point attained by the projectile before it strikes the ground? So I'll zoom out a little bit. How high is that point right there? Well, there's no point. Is there any point in doing this if we can't confirm it in the simulation? It looks like we've got this tape measure here. Very cool. Okay, can I rotate this? How does this work? Yeah. So let me see, there's a crosshair. Let me set this on the, not the ground here. It's got to be at the, where the origin was. Remember I put the origin at the base of the pedestal? All right, from here to the highest point, also known as the apex. Of course, apex makes me think of a battle royale video game on Xbox that I may have spent an obscene number of hours playing in the last year or two. I shouldn't be admitting that. Okay. So, according to the simulation here, the highest point attained is almost 17 meters. It would have been more dramatic if we calculated that first, but let's see if we can reproduce that number using our kinematic equations. Can you memorize that? 16.9, it's very close to 17. So we go back to our set of equations here and ask ourselves which of these will get us to that answer. Oy. Well, do we know the amount of time it takes to go from the launch point to the apex? We certainly have not solved for that. So in this equation, we do not know what that time interval is, but also this equation doesn't have a displacement in it. What we're interested in right now is this displacement. We want the vertical displacement from launch point to apex. That's not even in this equation, so that's no good. What about this equation applied along the vertical axis? This would be delta y, which is what we want. We do know the vertical acceleration, that's the negative 9.8. And because we found the initial launch speed, we can now evaluate the initial y component of velocity, because we know the angle and we found the launch speed. So we can actually evaluate that, which means we do know this quantity for the vertical axis. And what about this quantity? It's implicit, but what is the final y component of velocity over the time interval from here to apex? Remember, at the apex is that one moment where the y velocity goes to 0. If you could watch the trajectory from the side, like if you were standing over here watching it, you would see the cannon go up, briefly stop, come back down. I say briefly, but it's an infinitesimal amount of time. So we actually do know the y velocity at the apex. That's something you should memorize, that the y component of velocity at the apex is 0. So this equation will get us to the quantity we want. We know everything in this equation between times t0 and t1, as I called it, except for the displacement. That's what we're solving for. Great. So let me adapt this equation to times t0 and t1 and the y-axis. You should memorize them like this, but know how to adapt them along a particular axis between two particular times. So the velocity at time 1 in the y direction squared minus the velocity at time 0 in the y direction squared equals 2 times the y acceleration times the y coordinate at time 1 minus the y coordinate at time 0. This is the displacement between launch and reaching the apex, specifically the displacement along the y-axis. Okay. And here's where we use our recent revelation that the velocity at the top of the trajectory in the y direction is 0. And right here we've got negative v naught squared sine squared theta. Right? I'm using this trig relation. Initial component in the y direction for the velocity vector is hypotenuse times the sine of theta. Okay? What's going to happen with this minus sign? Well, don't forget that the acceleration is negative g. And you know what? I'm just going to abbreviate this delta y for now. Let's just call that delta y. later we can plug this back in. Okay, so delta y, it seems, is, let's just divide by 2g. V naught squared sine squared theta over 2g. And now we can plug in numbers. Delta y equals, remember I solved for the velocity already, that was 11.96. I won't bother with units right now. Square that, sine squared of 65 degrees divided by 2 times 9.8. Now remember, delta y is equal to y1 minus y naught. So I'll plug that back in now. y1 minus y naught equals, and let's see what this extra displacement is. 11.96 squared times 65 sine squared divided by 2 divided by 9.8. See what I did there? I can do two divisions rather than enclose the denominator in parentheses. It equals 5.99, which is really close to 6. Okay, so that means y1, I can put the y initial on the other side now. y1 is y naught plus 6 meters. And remember, we started from a height of 11 meters, so that brings us up to 17 meters. I believe that was what we found in the with the tape measure tool in the simulation. So physically, you want to be able to understand that this is the extra displacement beyond your starting point. Does that make sense? You go 6 meters, you displace by 6 meters from your starting point. That's where you are at time 1. So your position at time 1 is your starting position plus that additional 6 meters. Okay? Now, is there anything else we could do with this problem? Yes, we could actually go back and solve for how long it's in the air, the time of flight. We could solve for the time it takes to get to the apex. We could solve even for the y component of velocity when it strikes the ground. Because if we knew the time of flight, we could just plug that into our equation for velocity. And after solving for time of flight, we could plug that in here and find the y component of velocity at that time. So there's still a number of things we could do here. But at every step, it does help guide your thinking if you keep in mind how many unknowns do we have, how many equations do we have to work with, things of that nature.
Let's pump out another one of these, but this time we'll change the variable that we're solving for, and I think I'd like to launch a piano this time. How about a car? Okay. I will put the pedestal up at 15 meters, a little higher. Let's put the target way out at 50 meters. And I will assume a given launch speed. So suppose we have to launch this vehicle from the cannon at 25 meters per second, which is over 50 miles an hour. Got to get this tape measure out of the way. All right, so if we know the height, we know the distance to the target, and we know the launch speed, what do we now have control over? Well, we have to figure out the necessary launch angle, because if I just pick any arbitrary launch angle, it's probably not going to work. Let's give this one a shot. Oh, surprisingly, really close to the proper angle. Okay. Well, let me show you something. What if we dropped, oops, this is supposed to stay at 25. What if I go down to a rather small angle, reset, how do I reset? Yeah. Something real small like this. Doesn't quite make it, but maybe if we raise it just a tad. Well, look at that. 5 degrees seems to work. But wasn't that other angle also close? Let me go back to a considerably larger angle. Okay, that's going to miss. Maybe if I go a little bit higher. 5 degrees worked, and it looks like 70 almost works. 65 sent it past the target. 70 had it come up a little short. Maybe there's an angle also between 60 and 70 that works, or 65 and 70. All right, you probably have some intuition about that if you've played much baseball or basketball. Like, let's say you're going for a layup, or you can kind of throw the basketball directly at the hoop, or you can make it go high and then come back down. It's like there's two trajectories that will work. So we're kind of going into this expecting to find two angles that are sufficient. So make a mental note: 15 meters high, 50 feet out is the target, and the launch speed is 25 meters per second. Since you're already familiar with the setup, I'll go a little more quickly with this one. This time we know the height, we know the launch speed, we know the distance to the target. What we don't know is the angle theta. So I'm just going to begin at the same starting place that I did before. I'll write my kinematic equation for position along the x-axis. I know that, let's see here, x, let's go with the same time labels as before. T0, I'll set that equal to 0 seconds. That's launch. And T1, I'll put land, which is short for hit the target. So the x-coordinate at time 1 minus the x-coordinate at time 0 equals, that's displacement, right? Notice I'm going with different notation this time because I'm not going to mess with finding the apex height. There's no need for a label for that point. So time 0, time 1, initial and final. Well, that would be the initial velocity along the x direction. Remember, this is since we're applying our kinematic equation along the x-axis, the v initial is the initial velocity along the x-axis, which is the x component of the initial velocity. Remember, just like before, we can break this into components. The initial velocity vector has two components. All right, and this would be t1 minus t0 plus 1/2 at squared, except I don't need the 1/2 at squared because ignoring air drag means there's no component of acceleration horizontally. Gravity is straight down. Well, t0 was set equal to 0 seconds, so that's gone. And x1 minus x0, well, if I put my origin down here, let's say this is my coordinate system, then my final x-coordinate is positive d, my initial x-coordinate is 0, so the displacement is positive d. And now we can solve for the time in terms of the distance to the target and the initial component of the velocity. We do not know this component. Despite the fact that we know the speed, remember I didn't write these numbers down, but that was 25 meters per second. We know the hypotenuse, but we don't know what the adjacent component is because we don't know the angle. That's what we're looking for. And previously it was, oh, I got to sneeze here. In the previous example, we got to the answer by writing the kinematic equation for the y-coordinate as well. So let me do that, just trusting that that's the way forward here. So the y-coordinate at time 1 minus the y-coordinate at time 0, in other words, displacement along the y-axis, that would be the initial velocity at, or the initial velocity in the y component times t1 minus t0. This pen is finally running out of ink. And then we need the 1/2 at squared equation. There we go. Since I called up positive, my vertical acceleration is negative g, so minus 1/2 g times t1 minus t0 squared. But again, t0 is set equal to 0 seconds, so that's gone. And what is my displacement here? In going from launch to landing, well, I started at plus h units, and then I went down to 0. So my displacement is actually negative h. We went downwards by we went downwards by h units, which is a displacement of negative h. Okay, so this is going to equal v0 y t1, and I may as well substitute now for t1. Let's take this expression for t1, plug it in here, plug it in there. d over v0 x minus 1/2 g times, well, that would be d squared over v0 x squared. And this is the same place we arrived at in the previous example. The difference is last time we knew the angle. Remember, both of these components involve trig functions of theta. We knew the angle last time, and we were looking for the hypotenuse V0. Now we know the hypotenuse V0, and we are looking for the angle. And we're going to see that this requires just a little bit of extra cleverness in order to solve. So here's where I will use my expressions for the components. Both components of the initial velocity can be expressed in terms of the speed and the launch angle. Now, I could plug in V0 sine theta, V0 cos theta, but remember, V0 over V0 x, sorry, V0 y over V0 x, that's the opposite side divided by the adjacent side. In other words, that is the tangent of the angle. So how about I just substitute tangent right here for V0 y over V0 x? I've got negative h equals d tan theta minus, I've got a d squared times g, and downstairs is a 2. And unfortunately, this time, there's no nice cancellation. It is V0 squared cos squared theta. That's a minus sign right there. And we are solving for theta. Ugh. Yeesh. How do we solve this for theta? It's not something simple like tangent theta equals 5, and we can just take the inverse tangent of both sides. We've got two different trig functions within this equation. One of them is in a denominator, and it's also being squared. Well, maybe this doesn't appear to you immediately, but do you remember this trig identity? 1 plus the tangent squared of theta is equal to secant squared. Yeah, and secant squared is 1 over cosine squared. So this is 1 over cosine squared we have here. Can be written secant squared, but secant squared is 1 plus tangent squared. So we could actually write this as an equation in tangent. It would have a quadratic term, tangent squared, but maybe you're starting to see how this is actually a quadratic equation in tangent theta. So I'm going to rewrite this negative h equals d tan theta minus, and I'm going to ignore cosine squared for a second and write this as d squared g over 2 v0 squared. And then what I really have here is secant squared. 1 over cosine squared is secant squared, but secant squared is 1 plus tangent squared. 1 plus tangent squared. All right. And to make this easier to look at, let's introduce a variable. Instead of writing tan theta, let's just call it u. Let u equal tan theta. Now, what kind of angles are we talking about? This is a launch angle. Theta has to be between 0 and 90. We could launch it all the way up to 90 degrees. So our angle theta is in quadrant 1. What is the sign, SIGN, of tangent in quadrant 1? It's always negative. So u is a number between 0 and infinity, really. You might recall, if you look at a graph of tangent, at pi over 2 and negative pi over 2, tangent has asymptotes. So it's something like this, and then it skyrockets. That's the behavior of tangent of theta. Here, if this is theta, this is tan theta, which I'm calling u. So u could be anywhere between 0 and infinity. Okay, then we can write this equation as negative h equals d times u minus d squared g over 2 v0 squared. So what I'm doing now is distributing this garbage to everything inside. Minus d squared g over 2 v0 squared u squared. Okay. Well, this is a quadratic equation in u, believe it or not. So let me move this term to the other side. I'm going to put everything in standard form, meaning put the u squared term first, then u to the first power, then the constant. So I've got d squared g over 2 v0 squared u squared minus, then I'd have this minus du term, and then I would have a plus d squared g over 2 v0 squared minus h. I believe I'm doing this correctly. And at this point, oh, that's all equal to 0. So this is a quadratic equation in U. Don't be confused. This looks like the differential expression, du in calculus. It's not. It's distance to the target times the tangent of theta. I'm just writing the tangent of theta as this letter U. Rather than use the quadratic formula with this equation, let's make things simpler. I want to get rid of all this garbage. So I can multiply the whole equation. I'll say multiply by 2v0 squared over gd squared. Do you see that that would cancel this term? That would make the coefficient of the quadratic term 1, making it easier to implement the quadratic formula. It's almost always worth doing that. So after doing that, I get u squared minus, let's see here, if I multiply by all that, I would have a 2v0 squared over gd now, because one of the d's is canceled by the d that's already there, plus, okay, well, this just becomes 1. That's kind of cool. Minus 2v0 squared h over gd squared, and that's got to equal 0. Ultimately, what are we doing? Oh, there's a u in front here. We are going to find the roots of this equation. There will be 2 roots because it's quadratic. Remember, if one of the roots comes out imaginary, then the other one has to be imaginary as well, or I should say complex. So I'm expecting 2 real roots. Let me plug in numbers. And I think I have to go back to the... No, I've got the numbers here. Remember, V0, I decided was going to be 25 meters per second. We're going to launch from a height of 15 meters this time. And the target is going to be 50 meters away. So let me figure out what these various coefficients are. This coefficient right here, 2 times the speed of 25 squared divided by 9.8 divided by 50 meters to the target. So that's minus 2.5510. I'm keeping extra digits for now. Plus 1 minus, and then I think I've got the same 2.5510 here, but times the height. 2.5510 times this quantity h, which is 15. And you know what? I feel like I made a mistake. I did, because I did this already and the numbers don't seem familiar. This is actually not the same. I've got an extra factor of d there. Okay, fine. I'll just recalculate this. 2 times 25 squared times the height of 15 divided by 9.8 divided by 50 squared. That looks familiar. 0.7653. Of course, we can combine these two. Okay. And this ends up being 0.2347. Okay. The two roots of this equation will give us the 2 possible values of tangent theta that will get that cannon or piano or whatever it was that I launched to the target. So I'm going to cheat now. I don't have a quadratic formula routine on this calculator. I'll just pull up a website and put these numbers in. Okay, I've already entered the numbers. I just typed in quadratic formula calculator and used one of the first hits that came up. So I put in my coefficients. Remember, I had u squared, which means the coefficient of u squared was 1. This is the linear coefficient and the constant. After typing those numbers in and hitting calculate, it pumped out the 2 roots right here. So remember, this is not theta, this is u. These are the 2 values of u. I'm going to write those down. U is equal to 2.455 or 0.0956. So I've just written down these 2 roots. Remember, we're in quadrant 1 for the angle, so it makes sense that the tangent would be a positive number in both cases. Here are the 2 roots. And remember, u is equal to the tangent of theta, so theta is equal to the inverse tan, not the cotangent, no relation, inverse tangent of u. So we could take the inverse tangent of this number or the inverse tangent of this number, and both of those angles evidently are valid. So I'll start with 2.455. Make sure I'm in degree mode. Yes. Okay, that angle would have to be 67.8. That sounds about right, because remember when I was tinkering with the simulation, it was an angle between 65 and 70 that got us close to the target. The other angle would be the inverse tangent of 0.0956, which is really close to 5 degrees, and we found that 5 degrees actually did get it onto the target. Maybe not the bullseye, so I'm going to go back and just check these two angles. Okay, once more. 67.8. Well, I can't get any closer to that than 70, right? I can do 65 or 70. 70 is going to have to be it. And that's right, it falls a little short. So can you kind of sense that if we went down to 68 or 67.8, we'd spend a little more time? I shouldn't say we'd spend more time in the air. We'd have more forward velocity, and that's what would bring us to the target. The other angle was 5.46, which is pretty darn close to 5. Oh, I changed the speed, not the angle. Excuse me, 25 meters per second and 5 degrees. That's more like it. There it is.